Up to now, we've been focused in on finding areas of regions bounded by curves. But what if we want to extend what we've been doing and calculate the volumes of solids? So we've got a couple of methods for computing volumes of solids. And this first section that we're going to look at is a method where we slice the solid up into slices in order to compute the volume. So let's talk about what that looks like generally, and then we'll derive the formula. So if we have a solid, so I've got a little solid right here, in some ways you can think of it like a loaf of bread. Like if I have a loaf of bread and it's bounded between x equals a and x equals b, and we wanted to calculate the volume of that solid, what we're going to do is we're going to divide up the interval from a to b into n subintervals. And this should seem familiar. We do this quite a bit. So we divide the interval we're looking at, a to b, into n subintervals of width delta x, which will be b minus a over n. And then on each of those subintervals, on each subinterval, we're going to take a slice of the solid and calculate the volume of that solid. Or of that slice, I should say. It is its own little mini solid, but it is a slice of the larger solid we're looking at. So let's just focus in on, I don't know, this little subinterval right here. So on this little subinterval, we're going to come in here and we're going to slice it. Like remember that loaf of bread I mentioned just a second ago? We're literally going to slice this solid, up into little slices. Now the width of each little slice is going to be delta x. And what we're going to do is we're going to generate a formula. We're going to find a function, a of x, that's going to represent the area of a cross-sectional slice. So when we take this slice, the area of a cross-sectional slice, whoa, I just erased my picture. I put too much scribbles and I think it thought I wanted to erase. Let's not do as much scribbles. We're going to take, or create, I should say, based on the definition of the solid, how the solid is defined by curves within the x and the y coordinate system. But we're going to come up with a formula for the area, the area of a cross-sectional slice. So if that's the area of a cross-sectional slice, then the volume of every slice, then the volume of each slice can be found by taking the area of a cross-sectional slice somewhere on the interval and multiplying by the width. That's what the volume of each slice is going to be equal to. But we want the volume of, I should say that's the volume on the ith interval. But we want the volume across the entire solid. So if we want the volume across the entire solid, what we're going to do is we're going to add up, just like when we were finding areas, we're going to add up the volume of each slice and let n go to infinity. So if we want the volume of the total solid, what we're going to do is we're going to cut it up into little slices. We're going to calculate, let's get my highlighter, we're going to calculate the volume of each slice by looking at an area times a width. That's going to give us the volume. And then we're going to add all of those up from I equals 1 to n. of A of x sub I star. Now I'm using that little star because when we calculate that slice of that area, it doesn't matter where we do it because we're going to let this delta x go to 0. Then we multiply by the width of each slice, and we're going to let n go to infinity. By letting n go to infinity, that delta x, that thickness of each slice, essentially think of that loaf of bread analogy again. We're slicing the slices infinitely thin is what we're doing. We let the width of each slice get infinitely thin. As n goes to infinity, the width of the slices. As the number of slices goes to infinity, the width of each slice goes to 0. And here, joy, oh joy, this is a Riemann sum. And we, by the definition of the definite integral, when we let n go to infinity, this becomes an integral from a to b of a of x dx, where again, a of x is simply equal to the area of a cross section. All right, so we won't spend our time in the Riemann sum, but that's where it comes. We won't spend the time doing, finite volumes. We're going to spend our time figuring out what is the actual volume. Instead of taking a finite sum and approximating the volume, we're going to calculate it exactly by using an integral. Okay, but to do that, we do have to write the area of each cross-sectional piece. So I've got some pretty pictures. Our book actually has a nice interactive picture that lets us see this a little better, but I wanted to derive where that formula comes from, and then I will pull up the picture so we can see it. Let's start with this fun picture. This is a picture of a loaf of bread being sliced up, and you can see that cross-sectional area, A of x. And if we want the volume of that loaf of bread, we add up all those slices and let the number of slices go to infinity, giving us the integral that we just derived above. So that's first just kind of a fun little image to see what we're talking about. But let's go ahead and look at one that can be interactive from the interactive ebook. All right, so this is just from the interactive ebook. It's free to download the Mathematica player that will let you manipulate this. So remember, if you would like to see these images on your own, just go to our textbook in MyLab and open up the interactive e-text. So here we go. We've got a volume. You can see it right here. If we take now sort of, laid down so that we can see the interval from A to B, and we're taking n, I don't know, we can make n a little bit bigger, I guess. Let's make n right there. You can adjust n, and then you can see if we add up all those slices, and you can see the slices are changing as we go across that interval from A to B. If we can calculate the area of a cross section, come up with a formula for A of x, then the volume is going to be A of x times delta x, the width of each of those slices, and we'll add them all up. In this case, the book uses k. I was using I in my notation, but we just add those all up. K from a, running our k's from I equals 1 out to n, and as n goes up, that becomes thinner and thinner and thinner, and you can actually see that kind of that visualization in a static way right there. So as the number of slices increase, our volume calculation approaches the exact volume of the solid. Okay, so let's do a quick example. All right, so let's take this example. Suppose we have a solid, has a base that is in the region, or that is the region bounded by the two parabolas, y equals x squared and y equals 2 minus x squared. So before we get too much further, I just want to go ahead and draw what that base looks like in my rectangular coordinate plane. So I've got two parabolas. Those should be pretty easy to graph. All right, so there is the region that we're talking about. In terms of intersection points, I sort of did that based on just the parabola knowledge, but the intersection points, if I wanted to know what these two intersection points are, you can always set your two parabolas equal to each other. Remember to find intersection points. We can just set our two curves equal to each other, and solve, and we find that x is plus or minus 1. So at -1, we're at 1, and at 1, we are also at output value of 1. So this is 1, 1, and this is -1, 1. -1 and 1. So the solid, it says, is built because the cross section is perpendicular to the x-axis. Now this is going to be kind of hard because we're going to have to visualize this graph. I'm going to go ahead and erase the red here so we can see it. That's the region we're talking about. But in fact, you know what? Let's do it in highlighter. This is the base of the region. And then off of that base and perpendicular, so we do have to look at some of the terminology here, cross sections that are perpendicular to the x-axis. So that means that they're coming up the way I've drawn it. Because I'm working on a 2D surface, the way I've drawn it, they're coming up out of the board at us. So, you know, I'm going to draw it as best I can. I don't know, it's an interesting little square I drew. I'm going to draw it as best I can here. These are semicircles coming out of the board at us. And so these semicircles are building a solid, and I'm drawing a few of them. But the cross sections, so let's draw what a cross section, I'll show you a nice three-dimensional picture too. The cross sections, and they are perpendicular, so I'm drawing them perpendicular to the x-axis, are semicircles. They look like this coming out of the board. Okay? Okay, so what would that look like? Like, what would that solid look like? I mean, it's kind of a funky little solid. It's sitting on top of this page, if you will, but we can actually see a little visual because this is one of the problems from the book. So it does have a nice little interactive visual, and I'd like you to be able to see that too on this video. Okay, so this is being able to take what we had, that base. You can see the x and the y-axis on this graph. And this is taking that base, so you can see the x and the y-axis, taking that base and sort of laying it flat. And then you can see that solid, kind of that bubble, sitting on top of the xy coordinate system coming out at us. Where the cross sections, let's go ahead and do a slice, where the cross sections are semicircles, meaning a half of a circle. So right there in the shadow, you can see that semicircle. And let me just move it around. So you can see right there, see how it's moving. You can see at each spot, right, as we run across the base and take those cross sections, you can see they're changing, but they are always semicircles. Okay? And we do know how to find the area of a semicircle. It's just half the area of a circle. So we're going to go back to the notepad and we're going to actually work that and create the formula to calculate the volume here. But this is the solid that we're working with. We're working with a solid who has a base bounded by those two parabolas, and then built up off of the base are those semicircles. Okay, so let's get back to my more rudimentary drawing, but still working. So the area of a cross section, because it is a semicircle, it's 1/2 the area, meaning half of a circle, it's 1/2 the area of a circle. Well, the area of a circle is simply pi times the radius squared. So what would that be? Well, the radius of this semicircle, let's draw it right here, is this length. Which, by the way, the radius is always, I'll do it in a highlighter, here's the diameter. The radius is always 1/2 of the diameter of the circle. Well, how do we find the diameter of the circle? Well, let's come back up to one of our drawings up here on our solid that we were demonstrating. So the diameter is the length from the lower parabola to the upper parabola. So the diameter is going to be the parabola on top. Which was the parabola on top? Let's label these. This was y equals 2 minus x squared, and this parabola down here was y equals x squared. So our diameter is actually going to be, I'll do it in red, our diameter is actually going to be 2 minus x squared minus x squared. And our radius, let me highlight that. So I'm filling in as we go. So there's our diameter. Our radius is half of that because we're looking for the radius. So the radius is 1/2 2 minus 2x squared, which is convenient that there's that common factor of 2 because that's just 1 minus x squared. So the area of a cross section of this solid, based on how it was described, how it is built, is 1/2 pi times the radius, which is 1 minus x squared. And that is what I need in order to set up my volume integral. Because if I can find the volume of the solid by taking the integral from a to b. Well, this solid lives in between -1 and 1. So it's good. Well, let's write the general formula. A to b of the area of a cross section times dx. So the volume here, plugging in to our formula, our solid lies between -1 and 1, and our area formula is 1/2 pi times 1 minus, oh, I lost my square. Let me put it here in black. I just didn't write it. So let's correct that right now. So it's 1/2 pi times the radius, 1 minus x squared squared. Okay. Make sure we catch that as we go. Okay, we got to square the radius if we want the area of a circle. All right. And that's all I need. Now I can go ahead and do the calculation. So let's go ahead, let's expand out. Let's zoom in here. Let's expand out our square. We're squaring a binomial there. So this is going to be, I'm going to go ahead and write that. I'm going to pull that pi over 2 to the front. So this is pi over 2 in the front, -1 to 1. This becomes 1 minus 2x squared plus x to the 4th when I square that binomial. Remember, don't get caught in that little common algebra error that I see all the way through the calculuses. Don't forget that that means that we're squaring, right? So we're multiplying that binomial all the way out. Okay, so this becomes pi over 2. We integrate. This is x minus 2/3 x cubed plus 1/5 x to the 5th, and we're evaluating that from -1 to 1. There we go. That is the volume of the solid described very specifically as having that base between the two parabolas and areas of cross sections being semicircles. So let's just remember that's going to be the goal of this whole section, is to come up with that area formula, figure out how is the solid built and what is the area of a cross section. Then once we know that, we can integrate across the bounds of the solid from a to b of that area of a cross section dx.